This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events, and we have actually two kinds of weekly events. So today is one of them, and this is a webinar. And if you want to find to learn more about our events, you can go to our website, datatalks.club/events, and you can find out more about the events we have. So today we have a webinar, which is a more technical presentation with slides, which we usually have on Tuesdays. Then we have a different type of event on Fridays, which is more like a live podcast where we talk on different topics. So if you want to find out more about the events we have, go to this website and you'll see the kind of events we prepared. So for example, this week, today we'll talk about deep learning for recommender systems. And on Friday, we will talk about transitioning from project management to data science. So check it out. So if you want to stay updated about our events, well, the first thing you can do is join our Slack, subscribe to our newsletter, and subscribe to our YouTube channel. And last but not least, today, during our workshop, webinar, sorry, you can ask questions. For that, you go to YouTube live chat, and there is a pinned message with a link. Just click on this link, and you can ask any question there. And at the end of the talk, we will take all the questions. So that's all, and the floor is yours.
Okay. First, of course, thank you for the invitation, Alexei. It's a pleasure to be here. I will share in the screen. Let me know if you see the screen now, the presentation.
Yes.
Okay, cool. So yes, we will talk about deep learning recommender systems from prototype to production, right? Like we will talk also about how we implemented it at OLX. So this is the outline for today. In the first half of the presentation, I will be the presenter, but then Ilia will join me. Like we'll talk in the second part about how we apply this solution at OLX. But in the first half, I will mention like some examples of deep learning solutions that exist. And I will focus on one of them, that is a neural item embeddings. That is the one that we use at OLX. And later on, Ilia will talk about how we use experimentation at OLX to prove value and how we move from a simple POC into a productionized model that is highly automated. So this is us. You can see Ilia Ivanov is a data scientist working at OLX. My name is Cristian. I'm also a data scientist from OLX. I put there our emails in case you want to contact us if you have a question about the presentation or anything. And we work at OLX. As you can see, OLX is actually a group, and it includes many companies. We work for OLX Europe, but as you can see, there are the different brands, like more than 20 brands across the world. And we cover horizontals, like for example, we have in OLX Europe and Avito in Russia. But we also include like real estate, autos, and others. And something that is nice about this is that we had the opportunity to interact with data scientists working in other companies. Typically, they work on pretty similar problems. So from these kind of interactions, actually, the project that we will mention today was we were able to implement it thanks to this kind of interaction that we have. And so regarding recommender systems, this is probably obvious for most of you, but I wanted to point out that currently we interact with these kind of systems on a daily basis, right? In some cases, we maybe don't even realize, but if you go to Netflix or if you, for looking for a movie, or you go to TikTok, Facebook, you will have some kind of recommendation engine that makes your life easier. And probably we will see this kind of system more often, right? because there is an abundance of information on the internet, and we have many alternatives, and these are some kind of filters that we can use in order to be more efficient at finding what we are looking for, right? Maybe the one of the most common examples is the one from Amazon, but I include here because if you follow the link that I include in the slide, you will see that they are currently using neural networks for the recommendation engine. And Amazon is one of the pioneers regarding using this kind of system for the platform. Actually, the recommender system is at the core of their business. And it seems that at the beginning they were using, of course, matrix factorization. That was the state of the art for recommender systems for many years. But then they move on with started using neural networks. So yes, this is the main topic for the talk, is deep learning recommender systems, or DLRS for short. And just for you to know, there is a very famous conference that is called REXIS. It focuses on these kind of systems. And at the beginning, like, I don't know, 5 or 6 years ago, there was a side event called the DLRS, focused on the approaches that use deep learning. And nowadays, if you see REXIS, I was able to participate last year. You will see that actually now most of the works are applying some kind of neural network, of deep neural network. Okay, so and also companies are using this kind of techniques. So in this section, I wanted to show you a few examples of these methods, just to have an idea of what we talk when we say deep learning recommender systems. So the first work is from Spotify. Is the research team working at Spotify in the year 2013. They decided to use a convolutional neural network in order to generate an embedding representation of the song. So they have audio signals that they were encoding in a time frequency fashion, and they input this information into a CNN, and this model outputs a vector that is a representation of the song. And using this, they were able to overcome the cold start problem that is very typical in this kind of problems, right? The idea is that if you have a new song that you don't have enough information about this song, then a classical approach like collaborative filtering will fail, okay, because it needs some kind of history and interactions from users in order to understand how to generate recommendations for this example, right? Then in 2015, a research team from Yahoo came up with this idea of applying the same concept from word to back in the context of recommendations. So instead of generating embeddings of words, they were generating embeddings of products. And the idea was pretty simple. They basically train a word-to-back model in which they replace words by product IDs, and the sentences in this context would be purchase sequences from a user. And they use skipgram in order to generate these embeddings. Then in 2016, you have a team from Google Play, and they had the idea of combining two different models. In this case, the model that you see on the right is a deep neural network that they train using also embeddings. And the idea is to optimize this network for generalization. But they also include another model that is a wide linear model. It was trained on the feature transformation from a generic recommender system in order to to memorize these interactions, right? So they have the two different approaches. Like one is more focused on memorization, the other one more on generalization. And by combining these two models, they achieve a better solution. Then we have the session-based approaches. Like this one is from 2016. And the idea was to input sequences of items in a session into a recurrent neural network architecture. And this model will output what will be the next item in the session. And something cool about this implementation also is that they started using loss function from ranking. In this case, they use a patient personalized ranking. So this is also something nice about deep learning in general, that you can play with different loss function. And in this case, it is good because if you think about the problem of recommendations, you can frame it as a ranking problem, right? You have, for example, in item-to-item recommendations, you have one item, and then you want to rank all the other items in such a way that the ones in the top are the most relevant. Finally, this is a work from a team working at Pinterest. This model is called PinSage, and in this case, they decided to use a graph convolutional neural network in order to also generate embeddings of items. For example, you can see here the input graph and a target node, sorry. They have a target node A, okay, that is an item, or in the case of Pinterest, is a pin. And to generate the embedding of this item, they use the neighbor nodes, right? The ones that are close in this graph to the node A. And using this information from the neighbors, they were able to improve the quality of these embeddings. And so, and for example, if you go to, again, coming back to this conference Rexis, like in the last session of Rexis, there were many approaches using this kind of models, okay, because you are able to not only model the item, but also the relationship with other items. So to summarize some benefits of using deep neural networks, we can mention that you can extract deep features directly from the content. This is a nice features from this kind of models, because I showed that Spotify was extracting embedding representation from audio songs, but you can use the same approach and extract embeddings from images using CNNs, or embeddings from text using LSTMs. Then you can combine the information that you extract from those different sources very easily. And this is another good thing about deep neural networks, that it allows you to deal with heterogeneous inputs, right? Like are typically in the context of recommendations. You have images, you have text, you have categorical features, numerical, like the price of the item and so. Also, it allows to generate more accurate representation of users and items. I showed that some approaches were generating embeddings of items, but you can also apply the same approach and represent the user in this embedding space. And finally, you can use custom loss function, like the one that I showed before for ranking, that allows you to model this problem more accurately. Now, I will focus on one of the approaches that I mentioned before, that is the neural item embeddings. Yes, so this idea of generating item embeddings is not new, actually. If you see an approach like matrix factorization, okay, they were also generating embeddings of items. But in the case of deep learning, this idea started probably with in 2015. You can see here with this paper that is e-commerce in your inbox from Yahoo research team. I showed this before. So the idea is use a word-to-back algorithm to learn embeddings representation of products. But then in 2016, for example, we have Meta Pro2Back that is from the team working at Criteo, and they incorporated metadata or site information about the items into the Pro2Back model. And the idea was to use this to overcome the cold start problem that I mentioned before. Then 2018, we can see this work from a team working at Finn. Finn is a marketplace from Norway, and in which they applied also very similar idea based on the previous two, but they basically were using different models like a CNN on images to generate embeddings of the images. They use CNN on text also to generate embeddings of text and so on. And also they included some information from user behavior, like real interactions, to train a collaborative filtering model. And they use this also as input for the model. They concatenated all these embeddings, and then using a deep neural network, they reduced the dimensionality of the vector. And this is the input for the recommender system. And I mentioned this works because in 2019, a team from Avito, okay, that is one of the companies that are part of OLX group, they decided to implement this model that they called item-to-back. Just a side note, there is another model called item-to-back from the team working at Microsoft, but this is a similar model, okay, to Pro2Back, okay. But the one that from the team from Avito is different in the sense that, as you can see, the input of the model are attributes from the item, but it doesn't include information about the interactions from the item, right? Behavioral features. So because of this model, you can consider as a content-based model, right? So it is very useful in the context of cold start. And they tried this model, and they achieved very good results, as you can see here. 30% increase in contacts from item to item recommendations, and 20% increase in contacts from personal recommendations. So we talked to them, and we decided to implement the same idea, the same model for OLX Europe. And this is what we're going to talk now. So I wanted to show you how we generate these embeddings, right? So on the left side, we have an item, like this case is an iPhone, and the item contains different attributes. And we want to map this item into a vector in the embedding space, right? In order to do so, we use a neural network. This neural network first takes the text from the item, that is a concatenation of the title, the category name, and the description. We take the first 15 words of this text and generate word embeddings that then we pass to a LSTM layer. And this layer is the one that outputs the vector representation of all the text included in the item. Then we take the category, and again, we generate embeddings for each category. And this is the category of the product, right? And we also generate embeddings for locations that it includes a city ID, region ID, and so on. And in the case of the params, this is a field that contains a lot of information, but is quite sparse. So in this case, we use a dense layer to generate a vector representation of this information. Just to give you an idea, like for example, in the case of category cars. Params contain probably the maker of the car, the mileage, the price of the car. But in the case of the category jobs, it can contain the salary of the job, right? So depending on the category, you will have different values here. Then we concatenate the output of all these layers into a huge vector, okay, that has around, I think, 1,000 dimensions. And we use the same approach as before. Basically, we stack different layers in order to reduce the dimensionality of this vector. And we add also a dropout layer in order to regularize the network. But at the end, this model will output a vector of 128 dimensions that represent the item. And this explains how we generate the embedding for one item, right? But maybe you are wondering, okay, but how we generate the items in general, right? So in order to understand this, first, I want to talk about this similarity assumption. So we have this x-axis that represents time. And this is a user session, okay? It's a fake one. But the idea is that this user was interested in an iPhone and contacted these two sellers. And then we have another session in which the user was interested in some games and then contacted these three different sellers, right? So the assumption is that the contacts that happen within the same session, the same user session, are similar. So we can create pairs of items that we believe that are similar. For example, the pair number one is these two items, and then we will generate two more pairs based on the second session. And of course, this assumption can be wrong, but if we average the information from many sessions, we will have something useful. So then we have these two items. Again, we collected a lot of pairs that we know that are similar, or we assume that they are similar. So what we do is to feed the neural network with information from these two items. Okay, we call the first one the anchor item, and the next one the positive pair. Okay, and then this will produce two vectors. Okay, and if we calculate the dot product between these two items, we will have a score that represents the similarity between these two items. But we need some negative examples also. So it's very common to apply this technique that is negative sampling. We basically sample at random some negative examples. And again, we produce the embedding and using the neural networks, and we calculate the similarity using dot product. And then the objective will be to have the score between items A and P to be close to 1, because we assume that they are similar, and to make the score from A and N to be close to 0, because we assume that they are not similar. So to do so, we use this loss function that is cross entropy. And as you can see, we are basically passing the vector of scores and a target vector that has a 1 only in the first position and zeros on the rest. And in practice, we don't sample only one negative example. We sample many of them, and we apply some optimization in order to find actually the top 50 that are the more similar to the anchor item. Okay, and we call this the hard negatives. Doing this, we saw that the training, there is a speed up on the training. Okay, the network is able to learn much faster. Then, just to finalize, once we have all these embeddings mapped into the embedding space, okay, once we run this training, like the effect is that items that are close in this embedding space will be similar in some sense, like the neural network will learn the relationship between them. And the items that are more different or not similar, they will be distant to each other, right? So in order to generate recommendations, we only need to see for each item, what are the neighbors in this embedding space? And these are basically the recommendations that we will generate. So these are some reference from the papers that I mentioned before. And now it's a turn of Ilia. He will talk about the second part of the presentation.
Yeah, awesome. I have the control. Yes, cool. Yeah, hi everyone. Thanks, Chris. Thanks, Alexei, for the platform. And in the next half of the presentation, I'm going to share our experience with building and delivering to production the aforementioned item-to-vec models. But first, let's take a look at the similarity search problem, which is relevant here. So you have a collection of vectors or embeddings corresponding to the database of items on the platform. In case of item-to-vec, those embeddings are inferred using neural network that Cristian described before. And now for each new incoming item, you have to find the most similar ones by the similarity metric you defined as, and as it was mentioned, in our case, it's dot product. The problem is the search index is huge. In our case, in millions of items, can be even more. And so it takes quite some time to go through all of them to find the most similar ones. Instead of doing this brute force search, you can actually compromise some precision by employing an approximate nearest neighbor algorithm, which will find maybe not the closest, but good enough neighbors of your item. And there are quite a few implementations of these algorithms, well optimized, that you can use. To mention a few, there is Face library from Facebook that also supports GPU, which is a nice feature. It's quite rare, I would say. Annoy from Spotify, NMSlib, and the same algorithm as in NMSlib is also implemented in the open distro for Elasticsearch, if you're familiar with that ecosystem. So for us, Face Index is working quite well. So we ended up using it. We tested the other ones too, but those didn't outperform Face in our use case. Yeah, so this is what we do for the similarity search. Now let's talk about experimentation, and there are two parts to it. The first is offline prototyping, and the second is online experimentation. Now, on the offline stage and the development of a prototype, on this page, I would like to highlight a few points or decisions we find the most important, and I would split those based on the two objectives we have at the prototype stage. And the first goal is obviously to get a decent model, but not to spend too much time and money on over-optimization. We also care about the development speed, of course. So there is this trade-off. And on the left side, speaking of the model quality, there is no argument that the data is the most important factor of the success. So you shouldn't neglect the data cleaning and preparation step. Then your loss function is another key ingredient you should pay enough attention to. In the case of item-to-vec, we had to play particularly with the negative sampling to make the model work. Next might be even more obvious, but not less important, is the focus, basically. Working on a single model that maybe serves only a part of the traffic on your platform can save you a lot of time, and at the same time simplify the modeling process and improve the quality of the model in the end. In case of e-commerce, you can work with a specific domain, which is a single category or of products or a single market. So that was the case for us. And lastly, a couple of generalizations you can use to speed up the process of prototyping, and that is generic feature encoders and automated feature selection. It may be worth not spending too much time over optimizing your model in this sense, because with a high chance the improvement will be marginal, and also it might not be transferable to the other domains, which is a big concern if you have to work with different data sources. Okay. So these are the things I wanted to highlight regarding the prototype stage. Now let's say we have a model and a service running to provide recommendations. Before running an A/B test on real users, we highly recommend testing the end results to make sure it looks as expected. And for that matter, we are using an internal framework to display the output of different recommenders to compare those and debug. And yeah, on the right, you can see how it might look like. It's quite a simple service that we are using internally. All right, now we see that everything is good on this end and we are ready to test our models online. So that would be the next logical step. And as you can expect, the online metric doesn't always look like the one from offline evaluation. And in the case of item2bag, we had to go through a couple of iterations to make the target metric green, as you can see on the slide, the time scale. As I mentioned before, we worked with only one model, solving only one category of products in the beginning. And only afterwards, when we got decent results with that one, over a few iterations, we moved forward with generalization of the approach to the other domains. And talking numbers, the models, depending on the domain, enabled us to generate from 10 to 30% more events, which is a huge uplift. We are more than happy about. But to get to that last stage with these all the models serving all the markets, we had to go through some processes to make the code and pipelines in particular scalable and maintainable. And that's what I'm going to talk about in the last couple of slides. So please bear with me a few more minutes. And first point is automatization. As the legacy of the initial prototype, we had a bunch of Jupyter notebooks that many of you might be familiar with. And those were run ad hoc in Amazon SageMaker, which is a great approach for fast iterations and analysis, but it's not very scalable and maintainable. So to tackle this problem, we simply compile all the necessary code into a single Python script to be run on request in Amazon Batch. In addition, we parameterize this script to enable it to run it easily for these different domains we have. And that's how we run it, just as a simple job there, just one command. In addition to that, to regularly update models, we automated the retraining process by the means of Airflow with the scheduler. At OLX, we actually have a wrapper around Airflow to make the work with it even more convenient. Right. Yeah, I think that's it on the automatization part. This is how it looks. In our case with item2bag. And the other part I want to talk about briefly is monitoring, which is another point. It's hard to diminish the importance of in ML engineering, particularly. And we can look at the monitoring from three perspectives or stages. First is the training step, when you train a model and evaluate it offline. To keep track of code versions, parameters, and metrics, we are using MLflow, which can also be used as a model registry to manage your models between like stage and production and so on. Second is the inference step, where the model is deployed and fed with the real-time data. Here we want to make sure that the data distribution doesn't change much, and our model prediction is consistent in time as well. That's what we are concerned about here. You can also set up triggers to react to the unexpected events quickly. For this, we're using New Relic, but something like Kibana could work as well. And finally, business metrics, probably the most important part. You don't want to drop these ones with the new deployments or outdated models. To monitor those, we are using Tableau, which should be familiar to any data analyst, I guess. And overall, this is how monitoring of these models looks like. In addition, I could also mention things like Grafana to monitor the computational performance and stability of the services working for this. And that will probably be it. In conclusion, I would like to leave you with a super short list of things to take out from this quite dense presentation, as we've talked about a lot of things today. And so in the end, to recap, deep learning for recommendation is hard, but it might not be so easy to implement and deliver. So start simple, do not over-optimize, and iterate on what you have by getting feedback, the most useful feedback from your users via A/B testing. I think on this note, it will be it. Thanks, everyone. And I can pass the mic to Alex, I guess.
Yeah, thanks. Thanks a lot. We have quite a few questions, and I want to remind everyone, if you want to ask a question, there is a link pinned in the live chat. So it's best to use that link for asking questions. And let's start. So the first question we have is that, so product embeddings are great, but what happens when the number of items in the catalog vocabulary size change? Do we need to retrain from scratch or not?
I can take it. This is a great question. And fortunately, with this model, one of the benefits is that you don't need to retrain it so often as you have to do with other models. Why? Because as I showed before, let me go back in the presentation. As I showed before, the input of the model, okay, here. So if you see here, the input of the model is at the attributes of the item. Sorry. Here, we pass the attribute of the item as input. So actually, it doesn't matter if it's a new item or it's an old one, because we can represent this item in the embedding space as soon as we get the information of the item. And because of this, it's very easy to overcome the cold start problem, right? Something that maybe we can mention is Ilia, maybe he can give more details, but we were also running some online experiment to try to figure out how often we need to retrain the model, okay? But right now, we are training it in a monthly basis. And we saw some increase on some uplift on the metrics when we retrain the model, okay? But we don't expect it to be that huge, right? We expect just maybe a minimal increment if we retrain it more often.
Thank you. So Andrei asks, So he says, I wonder how do you choose the size of the embedding for each input feature, for example, text, location, category for this model?
Yes, we play a little bit with these dimensions, but for example, something that we took into account is how many different dimensions have the original input. For example, in the case of category, we have a limited amount of categories, right? So it doesn't make sense to map it to I don't know to 1,000 dimensions. We can easily, encode the information from category in 32 dimensions, for example, or even in 16. So we played a little bit with this, reducing the dimension of the embeddings, and then offline we tested how was the change in the performance.
And,
basically, you just start with some intuition, and then when you have resources and time, you can do some hyperparameter search, right?
Yeah, and I guess another important thing is that we want these embeddings smaller, right? So the smaller the embeddings, the easier it is then to search for the nearest neighbors, right?
Yes, but on the other hand, there is a trade-off also on the performance. Like the smaller the embedding, typically also the performance will be worse.
Yeah, so basically, like you need to see, like to find this trade-off, like you do this by experimenting, right? By trying different things and seeing how it works.
Yes.
Okay. Do you combine this deep learning DLRS with collaborative filtering?
Yes, we do. Actually, we didn't mention it here, but we generate recommendations mainly on two parts of the platform. One is the homepage, and in the homepage we have a collaborative filtering model that produces recommendations. But basically, we show some percentage of collaborative filtering, like the standard approach, and some percentage of item to back. That is this model. And the same idea in the item page, we have a bundle of recommendations, and they are like interleaved recommendation from the two different recommenders.
And why do you need two?
Yeah, it's worth mentioning that this is actually the best combination. I mean, we tried to serve recommendations using only one model, like either these item to rec or CF, but these both variants work worse than combination of these two. But apparently, because of the diversity thing and these recommenders picking up different patterns from the behavioral data, and working best together. That's it.
Yeah, that's interesting. Thank you.
Yep.
So another question is when not to use neural networks. You see that everyone is so excited about neural networks. It's hype, but are there situations where you would not use a neural network?
Maybe in the context of recommender system, I can say that collaborative filtering is a very good solution, and typically it's difficult to find something better. And actually, it took some time for us to find something better, right? We tried other models like the FAM, and it didn't work. And I had to say that it makes sense in the context of OLX to use a deep neural network like this one, because we have a huge problem of cold start, right? We have many items that are very short-lived. So they are created and they are sold very quickly, and that's it. We cannot continue recommending this item. But if you have a catalog that is kind of static, like, I don't know, I assume Amazon, for example, maybe just collaborative filtering will work well, because you have enough information about your catalog in order to generate recommendations.
Okay, makes sense.
Yeah, I can only agree. I think in general in ML, in most of the cases, it's not worth using neural network from the beginning. Like it's better to start with something simpler, unless you're working with some unstructured data like voice, that it's hard to deal with that. neural networks nowadays.
Yeah. So another question. So I don't know if I pronounce name correctly, Jack. Yeah, sorry. So anyways, the question is, okay, no retraining. I think this is a follow-up question to the first one we had about fixed vocabulary size. So no retraining because you use context-based features. But if you're training on sessions, like Airbnb paper, should we retrain from scratch or not in this case?
So yes, I don't know which paper he mentioned. He said Airbnb. Sorry,
Yes, Airbnb paper.
Maybe I think that I know which paper he refers to, but we didn't include in this presentation. Yes, in the case that you are learning from, I mean, it depends. The thing is that, for example, in our case, we have this collaborative filtering model, and yes, we had to retrain it. It's not retraining, right? It's you recompute the matrix every 2 hours, because otherwise, if you have new items coming in, then you won't be able to generate recommendations. So I would say that it depends on the kind of approach that you use.
Yeah, I would add that I don't remember exactly this Airbnb approach, but in some cases you might employ some tricks to calculate item or user embedding online. It will be relatively difficult, but in some cases it's possible to infer these embeddings from new interactions, like history of this user item. But I think it's rarely used.
For those who are listening, so I think so the paper is real-time personalization using embeddings for search ranking at Airbnb, and there is also a blog post listing embeddings in search ranking. So I will just quickly post this to live chat.
Yes, the person that created this work is also the one that embedded Prot2Back. You know, it's the same person.
Yeah, I wanted to put it to live chat, but something doesn't work, so maybe next time. Anyways, can you talk a bit about offline evaluation of recommender systems? What are the metrics that you use?
Yep, I can jump into that one. So on the metrics, we're using quite accepted metrics, I would say. Like popular one says precision at K and recall at K. That's easy to understand and well correlated with the performance that you're trying to optimize of these models. Sometimes also it's handful to use some ranking metrics like NDCG to when you want to look like at a larger scale and larger list of recommendations. Yeah, those are, I think, the most ones. You don't probably want to explode the numbers of metrics, which will be hard to monitor. What I could also, I think, add to that list is some diversity metrics that you can use to measure the diversity of your recommendations. It's not something that we are doing right now, but yeah, often in recommendations, it might be a good thing to monitor.
Yeah, maybe just to add to what Ilia said, I will highly recommend to try to measure. You will define probably if you have one of the systems some offline metrics and try to link those metrics to your online experiment. Fortunately, we found that the evaluation that we were doing offline was highly correlated with what we achieved then in our A/B test. But it is not often. In some cases, it's not the case. So it's worth spending some time trying to reproduce the context of the A/B test in your local, right? Or not your local, in your offline experiments, right? Because that can help you to speed up the iteration of the model.
Okay, thank you. How can one improve such embedding-based model further? So what are the possible next steps for the model?
Yeah, I can mention a few, maybe Ilia, if you want to also to add some. But I would say that, for example, as you can see, we are not using images at all. Okay, we don't expect to add a lot of information because we are already, taking description, category, and so on. So probably we cannot extract much information from the images, but still we want to try it. And there are other ideas that we are exploring, like, for example, one of the questions was if we are still using collaborative filtering. Yes, we do. We combine the two models. But what if we input some behavioral information into the model also? Maybe that will allow us to avoid having to use two different models, right? Because we will have already the information there. And then you can, like in the case of Fin, they use attention layer in order to decide in which case they use behavioral information and in which case use the content information from the item.
Yeah, I think an obvious and simple thing that you can also do is play with these hyperparameters that you have a lot of in neural networks. And you can also use some pre-trained models, like for text, for instance, to embed your text, extracting some semantic information with no need to learn it from scratch, or you can fine tune it. Yeah.
Okay, thanks. How did you validate that the new model performs well on new domains? Did it require manually inspecting every domain, or not?
Yeah. So well, first of all, we looked at the offline metrics, obviously, but then at the online stage, running A/B testing, we evaluated everything, like for each domain separately. So each market, each category, we could measure the performance separately in isolation.
So basically just looking at offline metrics, right? Then, because you also mentioned this step where you would do some sort of like this testing tool where you would visually see actually the output. Do you also do this kind of testing for every new domain, or?
No, this debugging, I mean, it's not like necessary for every single model, but just when you deploy like a new release, yeah, it's something that we might use. But I think here, yeah, the question is more about the performance, like the quality of these models. And yeah, for that, like the end metric will be these A/B tests results and business metrics. And then, so yeah, and of course, yeah, we did evaluate it that way. And it's quite natural and it's not so easy to implement.
Yes, one more thing also is at OLX we have our own internal tool for A/B testing, and it allows us to visualize many metrics during the experiments, right? And after the experiment, we typically run an ad hoc analysis of the data from the experiment. And in this case, we split the data in different dimensions, like the categories, but other dimensions like type of product, the price, and so. And we try to see how the model perform on each of these slices. And thanks to this, for example, we were able also to improve the model because we found that in some cases, for example, I can mention one example. When the title was short, we found out that the model was not performing very well, and we had to come with a workaround in order to improve this problem.
Okay, yeah, thank you. So another question is, so the question says maybe I missed the answer, but actually I don't remember if you covered that as well. So what is the best, so in this example, so this is item to item similarity recommendations. But what is the best architecture if you also want to take user history into account? And I think actually, because of the way you trained the model, you did take history into account, but maybe there are other ways, and maybe you can mention this briefly as well, just to remind.
Yeah, but it's true. What we described is item to item recommender system, but yeah, you can easily use it as a user to item recommender by treating your user as a set of items that user interacted with. To just take the history, but also what helped us is to use a DPA based on the lag between these items. So it's like the most recent items user interacted with, they get more weight. And yeah, basically those are the seed ads that we then use seed items to find the most similar ones, and then we combine those results into one for this user. Yeah, the question also mentioned like the best architecture. Unfortunately, I think I'm not certified to answer that one, but,
yeah,
but that's what we are doing.
I will try also maybe a recurrent neural network approach in this case, because we are trying to model, this sequence of items, of purchases or whatever. But yes, there are many different ways of generating recommendations for users. Once you already have a system to recommend things based on an item, right? One idea is what Ilia mentioned, like represent the user as the history of past interactions of past items. But you can also like generate an embedding representation of the user based on the history. And this is, for example, if you want to see this, there are many approaches. Like one is the YouTube recommender. If you look the paper, you will see how they use the history of the user in order to represent also the user.
No, thanks. So what we do is basically, as I understood, just to summarize, so we use the same model, we just represent user as a bunch of vectors giving more weight to most recent interactions, right?
Mm-hmm.
Okay.
Yep.
What do you think about predicting all unseen items for all users? What are the best practices for user-based recommendations?
I don't know if I understood the question, sorry.
So yeah, this is, I also don't know what actually, what it...
Sounds like user to item collaborative filtering, but not sure.
So what are the best practices for user-based recommendations?
If the scale is not too big, I think just factorizing user to item matrix will be like the best approach. It's something like ALS optimization.
Yeah.
And if it is, then I don't know, nearest neighbors or something like that.
Yeah, the approach that we just described works well enough. Yeah.
Does training with positive negative samples beat embeddings obtained from autoencoders?
We didn't try autoencoders, unfortunately, but yes, if there is a suggestion that this architecture could perform better, we will try it. Yes.
Okay, thank you. Question to Ilia from Rodney. Hi, Rodney. So any particular tool that you use for generic feature scoring and automated feature selection?
Yeah, it's a good one. I think it was generic feature encoders. Yeah, so that for the first one, now as far as I'm concerned, like we don't use any specific tool for that. It's just an internal implementation, but there is nothing like fancy. It's just some categorical encoders, but you can definitely like play with it more using some like frequency encoders and so on. We didn't invest too much time into it. And on feature selection as well, we just use some heuristic, some primitive ones, yeah, because we didn't want to spend too much time. But there are tools you can use that actually score your functions based on the subset of features, right? It would just take us too much iterations, I guess. But it's definitely something you can use if you have time and resources. But in case of neural networks, especially, it's just quite expensive. It takes like hours to train one model, and then you want to change like one parameter and retrain it. It costs something.
Okay. Well, I know that Cristian, you need to go now, so I think we should be wrapping up. So thanks a lot for joining us today and sharing sharing this all this knowledge with us and all this experience from Willix. And thanks also everyone for attending this, for watching the talk. And I don't know, maybe you have any last words before we leave?
Oh, thank you very much again for the invitation. It was a pleasure, and yes, if we have a way to continue the discussions, please let us know. Like if you have further questions.
Yes. So how people can find you? So you mentioned emails at the beginning. Some other Twitter.
We have
maybe
a Twitter account. We have the email. I don't know, LinkedIn.
Data Talks
They can
Club,
reach
Slack,
you
maybe?
for sure. They can reach you, and then you can redirect them to us.
Okay, I will. I promise to do that. Okay.
Yeah.
Well, that's it for today then. Thanks everyone for joining, and have a nice evening, everybody.
Thanks. Bye.
Or day, or yeah. So depending on where you're from. So goodbye.
Bye.